Okay, we're off to the next chapter here, which is chapter 8 and gases. So obviously in this chapter, we're going to talk about gases. We're going to talk about gas laws. We'll do some gas stoichiometry to go with all the other stoichiometry that we've been doing. So obviously gases are the state of matter where pretty much everybody has broken apart from one another. They're flying around. There's collisions that's occurring. And it's really those collisions, as we'll talk about in this chapter, which accounts for the pressure that we associate with gases, collisions with the container. In some cases, could be collisions with other gases, but mainly the collisions with the container is really what we see in terms of the pressure. And the more collisions, as we'll talk about, really the sort of increase in pressure that we see. Obviously, the least or less number of collisions, then obviously we do have a decrease in pressure that we typically will see. So let's start with obviously some substances that under sort of normal conditions are sort of in the gas phase. And when we talk about normal conditions, a lot of times it is not to be confused with something else we'll talk about in this chapter, which is sort of standard conditions. But under sort of normal conditions, that's kind of like room temperature type conditions, is conditions that typically, we kind of consider everyday type of conditions. And that's usually a atmosphere of 1 atmosphere, which is a unit of pressure, and usually about 25 degrees Celsius, which is our normal sort of temperature. Now, under these sort of normal conditions, sort of everyday sort of temperatures and pressures, ionic compounds really tend not to exist as a gas under these conditions. Ionic compounds, as we talked about a number of times throughout the semester so far, again, are our metals and nonmetals together. They are ions. We have our cations and our anions, and they are held together by really strong electrostatic attraction. And that is the attraction, obviously, that holds together the positive and negative charged ions together. That is a really, really strong sort of interaction. Frankly, it's one of the strongest interactions you could have, is that sort of positive negative attraction. And that means it takes a lot of energy if you want to sort of separate those guys out into the gas phase. And under most conditions, it does not happen. What usually will happen before that even happens is basically you could heat the heck out of it and it will just kind of start to melt rather than kind of go into the gas phase. Like some of those earlier experiments where you evaporate off to the water and stuff like that, if you let yours go for a while, you can kind of see it maybe melting rather than the solid that was left over sort of evaporating. And those were, again, ionic compounds like silver chloride and some of that tin oxide that we made. They would really start to melt before they would do that. So other compounds, though, do behave a little bit differently. And these other compounds are really, the difference is we have sharing of electrons. So our more covalent compounds or molecular compounds, where their electrons are being shared between everybody, they can be sort of gases under normal conditions. So we do have things like carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, and methane. They're all gases under normal conditions. But even sort of molecular compounds and these guys that do share electrons, they are, a lot of them are solids at room temperature. The main difference, though, between, say, an ionic compound and a molecular compound is they're much easier sort of converted into a gas than, say, an ionic compound. Because really an ionic compound is being held together by intramolecular forces, that electrostatic attraction, which is really, really strong. It's very, very hard, again, to kind of turn it into a gas. Now, opposite of that, what holds together sort of molecular compounds, as we've sort of touched upon a little bit and we'll touch upon later on as well, what holds together sort of those type of compounds are what are referred to as intermolecular forces. And these intermolecular forces, for example, if we hold together, say, a water compound with another water compound, and because they are both polar molecules in this case, the oxygen being more negative, hydrogen being more positive in each of these guys, we get this sort of what is referred to as hydrogen bonding that happens between, say, 2 water molecules. Now, intermolecular forces are always much weaker than intramolecular forces. So it is much easier to turn something like water, which is a very prime example of this, into a gas. right? We just basically heat it up with some fire there, and as we get enough temperature there to get it to start to boil, and it'll go from the liquid state to the gas state really easily. And that's because to do that, instead of trying to break the entire molecules of water apart, what happens is that bond between different water molecules is much easily broken, and that takes a much lower boiling point to do that, like we say in water. And when you do that, the bond between the two water molecules actually is what takes them apart, and it breaks apart, and we get these water molecules that are able to, say, go into the gas phase there. Much easier than obviously something like an ionic compound, which is really something like, say, sodium chloride, which are a bunch of positive, negative ions, basically all stacked together, clumped together. And it takes a very lot of energy to try to get those guys, and it doesn't normally happen. So it really is this sort of intermolecular forces and intramolecular forces that sometimes does play a very big role in whether or not we could get something into the gas phase. And things with intermolecular forces can definitely get into the gas phase much easier. Now, that's something like hydrogen bonding. You could have something that is a nonpolar molecule that it uses something like dispersion forces, which is a super weak sort of interaction between molecules, and they could go into the gas phase much easier. Like when you open up the gas valve there and you got something like methane coming out, it goes into the gas phase very easily because they're using these very weak sort of forces that hold these molecules together. So it doesn't take a lot of convincing for them to basically be a gas. That's why a lot of organic compounds we'll talk about when we get to that sort of chapter as well, which are pretty much non-polar, uses those very weak interactions between molecules. And that's why a lot of those early sort of organic molecules are gases as they normally come. Things like methane, propane, butane, those are all sort of gases. Now, under normal conditions, our guys that we typically do see as gases, we have hydrogen, nitrogen, oxygen, fluorine, and chlorine. These are our diatomic sort of molecules, which are elements. So remember how these guys naturally come when they are uncombined is in this form, H2, N2, O2, F2, Cl2, and they're also gases. Ozone is also a gas. And obviously our noble gases there in group 8 are gases. They're sometimes referred to as being monoatomic, which means they typically come as ones rather than twos, like the guys that are up on top. So looking at our periodic table, again, pretty much these guys in blue is our area there where we have these guys under normal conditions coming up as gases. So let's talk a little bit about some characteristics of gases. Gases assume the volume and shape of their containers. And one of the things that we talk about a lot in this chapter is the idea of an ideal gas. And that is one of the sort of ideas of an ideal gas is that basically the gas molecule is flying around pretty much freely there in the container. And when we think about the volume of the gas itself, we really oftentimes will refer more so to the gas, the volume of the container rather than the gas itself, as it is moving sort of throughout that container sort of uniformly. Gases are the most compressible state of matter. Gases do mix evenly and completely when they're in the same container. And we'll talk about a little bit later on this chapter as well. Something else to make something sort of an ideal sort of gas is the idea that you could have multiple gases together in the same container, and there's very little sort of interaction between those gases in an ideal sort of situation. Gases have a much lower density than liquids and solids. Now, when we did density or talked about density, typically for liquids and solids, grams per milliliter or grams per cubic centimeter are your typical units that you find with liquids and solids. When you do get to sort of gases, the units that we typically use for density is grams per liter. So that's a sort of a different sort of unit. And that's a common unit that is used for the density of gases. And we're going to talk about how to calculate the density of a gas a little bit later on in this chapter. So there really are a few different sort of units that we come across a lot in sort of gases and sort of gas laws. But pressure is obviously the big sort of unit. And there's a number of different sort of pressure units that are sometimes used. A Pascal, which is a Newton meter, is what the N and the M squared stands for. Also, kilopascals is sometimes used in terms of units. But really, I would say for our class and most of the chemistry classes that you deal with, these are the big three, really, in terms of units that you do come across. And that's an atmosphere, which is an ATM. mmHg is millimeters of mercury. And torr is the other unit. And really, that's all based off of those two sort of units, if you will, are based off of this guy over here. That is a barometer, which is used to measure the pressure of gases, or the room pressure, really. And these are what a traditional barometer looks like. A lot of them here in schools are not like this anymore because they have mercury in it. But basically, a traditional sort of a barometer would have mercury in it. It'll have sort of a glass tube, and basically, as the atmospheric pressure exerts on the pool of mercury, the mercury here in the tube basically rises or lowers. And mercury is sort of unusual than some other sort of substances. And I think we might have touched upon it the other day, but mercury actually has a sort of reverse meniscus, kind of goes upwards in a sense. And that's because the attractive forces between mercury and itself, rather than mercury in the glass, are much stronger. So it kind of comes in on itself. And that's unusual, as most substances like water, the attraction between water and the glass is actually stronger. So it kind of goes upwards and makes kind of that meniscus going that way. If you ever come across a mercury barometer and it does curve that way, you actually read from the top of the meniscus in that particular case, which is a little bit different than obviously the bottom of the meniscus, where most liquids kind of do that curvature. You read from the bottom. So this is a barometer. It was invented by a guy named Torricelli, which is what this unit would represent. And this unit represents basically how you typically would take a reading on a barometer. On this tube, there's usually like a ruler, and you can measure basically the level there of mercury, like reading a ruler. A lot of times is in inches or centimeters of mercury, and it can be in millimeters. So that's what it is, basically millimeters, like reading a ruler. So millimeters of mercury, torr, and atmospheres, really sort of your most common sort of units of pressure that you come across. And other ones, obviously PSI, pounds per square inch, is another unit of pressure that is sometimes used. Also, a bar is another unit of pressure. So these are a few other units that you sometimes come across. A bar is almost like an atmosphere. It's like 1.01 to 1 sort of conversion. They're very, very close in it. But these three are really the ones that you see a most. And that means that we do need to be able to convert between these different units. And that 760 number there basically is our conversion factor to do that. So basically, if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760. And that will give you a torr or a millimeter of mercury. And vice versa, if you have a millimeter of mercury or a torr, you would divide by 760. Will give you an atmosphere. And that's because basically a millimeter of mercury is the same thing as a torr. It's a 1-to-1 relationship between those two. So just change the units. If you got to do that conversion, that's not too bad. But a torr and a millimeter of mercury basically are basically it's kind of the same unit. Any questions on that there? Now, obviously, depending the distance, say from sea level, or as sort of our distance increases, our pressure, as you can see, also decreases in that, right? Which is why when we fly on planes, they pressurize the place, right? So we don't have any sort of pressure problems. But as you can see, as the distance from sea level increases, we do see a decrease there in our pressure as we go up. So we're going to talk about some different gas laws here. And when we talk about gas law, there's really sort of three variables that we deal with a lot, and that is pressure, volume, and temperature. So pressure, volume, temperature are pretty much the three sort of variables that we see in most gas laws. And in a lot of gas laws, sometimes one of these are kept constant and we vary the others, or we may just vary all three of them in some cases. But these three ones here, pressure, volume, and temperature, are the three main sort of variables that we do deal with. So let's take a look at sort of our first one in a sense, or just a second here. But this is a equipment that you could use to measure the pressure of a gas, and this is a manometer. And it's basically has a couple of different ways. This is a closed sort of system in a vacuum. It's sort of closed there up on top. So obviously with this gas in here, it's got kind of nowhere to go. So it's going to push the mercury, and there's no atmospheric pressure coming back in on it from the outside, since it's a closed sort of system. So basically by measuring the height of the mercury in the column, you could figure out the pressure basically of the gas through that measurement. Now, when we have a more open system, which is what the difference is here, that is open, we do have to take into account the atmospheric pressure that's probably like pushing back down on it a little bit there through the opening. So in this particular case, same idea. The gas here obviously is going to fill the tube here, going to push on the mercury that's in the tube. But in this case, the pressure of the gas would be both the height of the column and also the correction there for the atmospheric pressure that would be pushing back down. So when we look at some gas law sort of relationships, the first one that we're going to look at is our good friend Boyle. And Boyle did a lot of sort of experiments with pressure and volume, and he kept constant temperature in this case. So what we see in sort of this relationship here with Boyle's law is, as the pressure sort of increases, we do see that the volume decreases, and we see that here in these sort of tubes. Here we have 100 milliliters versus 50 milliliters, and with 100 milliliters, larger volume, smaller pressure. Here, though, obviously we lower the volume, we see a much higher pressure. We lower the volume even more, we see a jump there in the pressure, as well as there's a much greater amount, obviously, of mercury there in the column than we had as we go there. And that makes sense if you sort of think about it. If we squeeze down the volume here of a gas molecules, that frankly means those gas molecules have very less room to fly around in, which means what that's going to do is increase the number of collisions. Increasing the number of collisions is going to increase the pressure that you're going to see. Obviously, if we go in sort of the opposite direction and increase the volume, give everybody a lot more room to fly around in. They're going to have a lot more room to fly around in, which means it's going to take longer for collisions to occur, and we will actually decrease the number of collisions, and we will see a decrease in the pressure as well. So kind of small, little room, more pressure, larger volume, less pressure that's going to basically occur in this situation. And that's what we see here on this, both graphs actually. Again, smaller volume, much larger pressure, larger volumes, much smaller pressure that's happening there. And there is a relationship that the pressure is proportional to 1 over the volume. And at constant temperature, we do get Boyle's law, which is this guy right here. This is P1 V1 is equal to P2 V2. And when you look at something like Boyle's law, there is also a relationship of, if you take the same gas and you do a bunch of pressure volume measurements at the same temperature, when you multiply the pressure times the volume, it will always equal the same number. And sometimes that's referred to as a proportionality constant. Sometimes it's like a little k that is equal to. And basically, you take any pressure volume combination, you'll get the same number. And that is why we basically could set them equal to each other. P1 V1 equals P2 V2. Now, the deal here with the pressures is it really can be any unit you want, as long as they're the same on both sides, so everything cancels out. And the same thing with the volume here. The volume can be any unit you want, again, as long as they are the same on both sides so that they cancel. And again, the relationship here As the volume increases, pressure goes down, and vice versa, volume going down, pressure going up. So that sort of opposite relationship that we see here. Any questions on that? And again, this is that constant temperature here. So let's take a look at one here. I think why don't you give it a go? We have a sample chlorine gas occupies 946 milliliters at 726 millimeters of mercury. What is the pressure when we go to 154 at? Okay, let's take a look. And one of the things that I would recommend is when you're doing gas law problems, sometimes the best thing to do is really just to pull out the information from the problem and sort of label what it is. And oftentimes it'll really point you in the right direction if you're not sure perhaps what gas law maybe to choose. Obviously, in this case, we've only have one so far, so that's probably the right one to choose. But obviously we will have more. So we do have some volume here. That's a 946 milliliters. We do have a pressure that's 726 millimeters of mercury. We're looking for another pressure, and we have a volume that is 154 milliliters. So again, you can kind of see obviously Boyles Law developing here, and that would be the sort of correct one to use in this particular case. Once again, you could call whichever one's ones and twos. It really doesn't matter as long as you obviously keep the units that go together still together with each other. So in this case, I'm going to be looking for P2. So with all gas laws, pretty much, if you're not sure how to properly rearrange these things, you basically, when you move something across the equal sign, it ends up in the opposite location, right? So we want to end up with this. It's really not a fraction in this case, but all these guys are up on top, which means this guy goes to the other side on the bottom, and that will give us that P1 V1 over V2. We're basically dividing by V2 is equal to P2 in this case. So put in our numbers here. We got 726 millimeters of mercury. We got 946 milliliters divided by 154 milliliters equals P2. This case, the units here are the same for our volume, so everything cancels out okay. Also leaves us millimeters of mercury as our unit, so 726 times a 946 divided by a $1.54. Gonna give us like a 4460, it looks like there. And that is going to be millimeters of mercury in this case. Any questions on that calculation? Again, understanding sort of the relationship that we talked about for something like Boyles Law can also help you in a sense of maybe you can make sure perhaps you didn't mess up the calculation too much. Here we do see that the volume here decreases, which means we should expect the pressure to increase in this case. So it went from 726 to 4,400. So that definitely is an increase. So that is a good thing. So sometimes it's good to keep that in mind as you go through it. I can't tell you how many times I've seen people inverse numbers when they're trying to rearrange equations. So again, just keeping that in mind, you know, does your answer sort of make sense when you do it? Any questions on there? Okay, then we're going to talk about some other gas laws here, which is not that one, apparently. I'm not sure where all my things went. There we go. Oh, I got one more, maybe. I do. Let's try this one. An inflated balloon at 0.55 liters at sea level at 1 atmosphere and rises to 6.5 kilometers, whereas the pressure is 0.4. What is Okay, let's take a look at this one. So again, if we pull out the information, we got a volume that is 0.55 liters. We have 1 atmosphere, that is a pressure. Rises to 6.5 kilometers, which is useful units here. We don't really need that for anything. We do have another pressure that is 0.4 atmospheres, and we are looking for a volume here. So once again, you can really hopefully see Boyles Law developing there in this case. And in this case, we are looking for V2, which means we're going to send P2 to the other side on the bottom. and dividing by it basically gives us P1 V1. If I know how to do numbering there, try that again. That's like a 1 equals V2. Putting in our numbers here, P1 going to be 1 atmosphere, V1 going to be 0.55 liters divided by our P2, which is 0.4 atmosphere. Once again, here we're okay in terms of units of our pressures. They're both in the same unit, so we don't have to worry about any type of conversion. But obviously, if one was 1 unit of pressure and one was a different, you would have to choose. And it doesn't really matter which one you choose as long as they are the same units, it will come out the same. So our atmospheres here will cancel. And that's going to get us basically a 0.55 divided by 0.4. In this particular case, our units that are left over are liters based off of that unit there. And that gives us 1.4 liters. Once again, understanding our sort of relationship in this problem, the pressure went down, which means we should expect the volume to go up. And in this case, it did. It went from 0.55 to 1.4. So again, if you didn't do the math wrong, at least you went in the right direction in that case. Yeah. Any questions on Boyles Law here? Okay, so now let's talk about the other sort of gas laws, or some other gas laws here. So Boyle dealt with pressure and volume, and now we're going to really look at a couple different relationships here. We're going to look at the relationship between volume and temperature, and we're going to keep pressure constant in that case. And we'll also look at the relationship between pressure and temperature, and we will keep volume constant in that particular case. So let's talk first off about what we would expect to sort of happen here in this situation here. So if we did have a gas that was in a container with a fixed volume, basically not moving around that volume, what would happen in this particular case is if I increase the temperature, would my gas molecules move faster or slower? If I increase temperature, they should move faster, right? Like you light a fire underneath somebody, right? They move faster. So as you increase the temperature, gas molecules are going to be moving around faster, which means they're going to be flying around in this container a lot faster. And that's going to cause a lot more collisions to occur. And what we would expect in this case is the pressure will actually go up. And that's because the volume is fixed. It's not going anywhere. It's hanging out pretty much in that spot. So in this particular case, if we were to increase the temperature, we would increase the number of collisions, and we would expect the pressure to basically go up. Now, the opposite is sort of true as well. If we lower the temperature, our gas molecules will then have less energy. And as they have less energy, they're going to be flying around slower. And as they're flying around slower in this container, again, it's going to take sort of longer for them to have collisions, and it will lower the number of collisions. And in terms of the pressure, what we would see in that case is the pressure will start to come down. So the relationship that we see here is as we lower the temperature, the pressure will lower in a situation where we keep the volume constant and basically have a fixed volume. Now, on the other end of the spectrum here on the left, we're going to look at volume and temperature. But in this particular case, we are going to keep pressure constant, which means that the volume here is frankly not constant. So if we take our same sort of gas molecule and we increase the temperature, as we just talked about on the other side, if the volume is fixed and doesn't move, we would expect basically a number of collisions to increase, and we would expect the pressures to start to go up. Now, in this particular case, we actually want to keep the pressure constant. So what happens in this case, when we do increase the temperature, we actually will see an increase in the volume as well. So because the volume here will start to increase, that gives that faster moving gas molecule a lot more space to fly around in. And what that's able to do is basically maintain the same number of collisions as it was previously. And that is how we keep the pressure constant in this case. So the volume basically adjusts to allow enough room to keep the number of collisions basically the same. And that is how we basically keep that pressure constant. The same sort of effect happens in this situation when we lower the temperature. When we lower temperature, much like on the right-hand side, if that volume was fixed and not moving, we would see a decrease in the pressure because of the less collisions. So what happens in that case is the volume actually helps out again. We actually will lower the volume or decrease the volume in that situation. And by decreasing the volume, what we now do is sort of trap that gas molecule in a much smaller volume. And that's going to keep the number of collisions up in that case to where it needs to be to keep the pressure constant. So in a situation where we're trying to keep constant pressure and we're changing the temperature, it is actually the volume and the adjustment of the volume that allows the pressure basically to maintain its constant value. And that doesn't happen, obviously, where you don't have that luxury because basically the volume's locked into place. If you increase the temperature, you get that direct relationship of more collisions and more pressure. And if you lower the temperature, you still get less collisions and a lower pressure in that situation. Any questions on relationships of those two guys? And that's what we see here. This is our volume temperature relationship at constant sort of pressure. And again, you can see in this particular case, lower temperature, we do see that lower volume of gas, again, to keep those collisions up. And here at a sort of higher temperature, we've got a larger volume there again to allow the number of collisions to remain constant. So these two relationships really go with two different gas law. As we'll see here on the next slide, this is our friend Charles' law, basically, and this is our friend Guy Lussac's law, which is sort of the pressure temperature relationship between these two. Now, there is also another sort of important aspect to both of these laws, and really all gas laws as well, that sort of came out of these experiments that were done by Charles' law, or Charles and Guy Lussac's. And when we look at a graph of any gas that you like at the volume and the temperature, it really doesn't matter the gas that you're looking at. If you take these sort of linear lines and extend all these lines back down to the temperature sort of spot, they all hit the exact same number, which is a temperature in Celsius of minus 273.15 degrees Celsius. That number should look familiar. That is the number we use to convert to Kelvin. Yes. So Kelvin recognized that, right? And called that absolute zero. And that is because if you have minus 273.15 degrees Celsius and want to convert it to Kelvin, you would add 273.15, gives you 0 Kelvin. Yes. So that is basically absolute zero, which is 0 Kelvin. The result of that is pretty much any gas law that you see, temperature always needs to be in Kelvin. So temperature, no matter what it is, always needs to be in Kelvin when you are dealing with basically a gas law. So Charles' law basically is our V1 over T1 equals V2 over T2. This again is at our constant pressure. So this is where we're going to get our volume to adjust to allow that pressure to stay constant. And once again, temperatures do need to be in Kelvin. And as the volume goes up, so does the temperature. And as the volume goes down, so does the temperature in that case. And our Guy Lussac's law over here is the one that deals with the pressure and temperature, which is very similar. P1 over T1 equals P2 over T2. This is at constant volume. And again here, temperature needs to be in Kelvin on both sides. And pretty much any gas law that you have needs to be in Kelvin. Now, that also includes very common problems that you find a lot of times in textbooks and sometimes throws people off. And that is, they will give you the temperatures in Celsius. They will ask for the answer in Celsius. So people just naturally assume that you could leave it in Celsius and put it into the gas law. But you do need to convert it from Celsius to Kelvin, go into the gas law, get your answer, and then convert it back to Celsius at the end. So you definitely always got to have in that Kelvin for the gas law. Even again, if you're given it in Celsius and they want the answer in Celsius, you got to do that conversion. So our relationship that we talked about on the previous slide there, as we increase the pressure, so does temperature. And as we decrease the pressure here, so does the temperature go along with that. Any questions on any of those there? All right, so let us try some of these good guys. Give this a go. A sample of carbon monoxide occupies 3.2 liters at 125. What temperature will it occupy at 154? Okay, let's take a look. So again, if we kind of pull out the information here, we got 3.2 liters. That definitely is a volume. We got 125, which is a temperature. And we're looking for another temperature here, and we have a volume of 1.54 liters. So once again, we do have a few to choose from at this point, and clearly this guy should look like the one that you kind of see there. We got a couple of volumes, a couple of temperatures. So our Charles law there would be really the right one to use. In terms of our volumes here, as long as they are the same units, you're good. So in this case, they are both in liters, so that's okay. And that also goes with Guy Lussac. As long as the pressures are both the same unit, it really doesn't matter as long as they are. But it is our temperature here that we definitely need to convert to Kelvin. So we'll add a 273 to it, and that's going to give us a 125 plus the 273, and I don't know, like a 398. Looks like a winner. 398 Kelvin. So in this case, we got a V1 T1 equals V2 T2. Again, I'll call these guys the ones, call these guys the twos. That means I'm actually solving for T2 in this case. That means I really need to multiply T2 to the other side, which means bring it over there. And really the guys on the left-hand side, I need to bring to the other side. So they're going to go there and there. So if I do that, I will do that in steps there. We'll get T2 to the other side equals our V2. And then again, we're going to bring over the other guys across, gives us V1 is equal to V2 and our V1 and T1 up on top there. So we got our guy rearranged correctly. Again, basically multiplying T to the other side, dividing the V1 to the other side, and multiplying the T1 to the other side. We'll bring them back across. Put in our numbers, gives us V1 is equal to our V2, which is 1.54 liters. And our T1, which is 398. And our V1, which is 3.20 liters. The liters here will cancel. We will end up with Kelvin. Going to give us 1.54 times the 398 divided by a 3.2. About a 192 Kelvin would be our answer here. That's good. If you wanted Celsius, you could subtract 273, and looks like we'll get like a negative 81.5 degrees Celsius. But Kelvin would be just fine, I think, in this question. Again, if we think about our relationship here, in this case, our volume went down. And in this Charles law relationship, that means that we should also see a decrease in temperature. And again, we did see that as it came down to 192 from 398. Any questions on that problem there? All right, try a couple more here. In an experiment, 452 milliliters of a gas was used in a light bulb. It went from 22 to 187 degrees Celsius. What is the final volume? Final pressure? Not final volume. One of those. Whatever it says there. V is volume, I think. Right? What is the final volume? So if we pull up the numbers here, we have 452, which is a volume. We got a temperature of 22 degrees Celsius. Then we take it to another temperature of 187. And we are looking for a volume there. So once again, just kind of labeling it like that, you should sort of be able to hopefully see sort of Charles law happening. And I'll call the first ones ones, second ones twos here. In this case, we do need to, like most and pretty much all gas laws convert our temperatures here to Kelvin. So we're going to add a 273 to each of those. So that's 22 plus 273. It was like a 295 Kelvin and a 187 plus a 273. Going to give us a 460 Kelvin. So now we got basically everybody in the correct units here. We're going to solve for V2. So V1, T1 equals V2 over T2. And we're going to solve for that. So we're just going to bring this guy to the opposite location. And that will give us V1 T2 over T1 is equal to V2. Popping in our numbers again in the correct spots here. V1 being 452 milliliters up on top. Our T2 being the 460 up on top. And 295 there on the bottom, Kelvin. Kelvin's going to cancel, going to leave us with milliliters when it's done. 452 times a 460 divided by a 295, going to give us about 705 milliliters in this case. Once again, looking at our relationship, we see in this case an increase in temperature. And based on this, we would expect an increase in volume to occur because of Charles' Law sort of relationship. And again, we went for 452 in this example to 705, which again is an increase in what we would expect to happen here. Any questions on that particular one there? And sig fig wise, normal sort of rules apply. Yeah. All right, one last one in this group here. Argon is an inert gas. We have a light bulb at 1.2 atmospheres at 18 degrees, heated to 85. What is the final pressure in? All right, so in this case, we do have a pressure that is 1.2 atmospheres. We have a temperature that is 18. And we have another temperature that's 85, and we are looking for a pressure in this case. So once again, you should hopefully be able to see sort of Lussac's law, which is P1 T1 equals P2 T2, as we got both of those things happening here. This is our constant temperature. I'm sorry, not constant temperature, constant volume situation. We call those ones, we'll call those twos. So in this particular case, we are solving for P2, which means we're going to send our T2 to the other side, gives us P1 T2 over T1 equals P2. We do need to, like pretty much normal here, get our temperatures into Kelvin. And in this case here, we'll end up with 358 and 291 here, I think. And now that we have that, our pressures in atmospheres just means that our answer will be in atmospheres when it's done. So putting in our numbers here, our P1, 1.2 atmospheres, our T2, which is 358, and our T1, which is 291. Once again, here, our kelvins are going to cancel, and it looks like 120, 358, and a 291 are about a 141.48 atmospheres in this case. And here we do see that the temperature increased. Temperature increased, which means we would expect the pressure to come up, and it did in this particular case. Yeah. Any questions on that relationship there? Charles' Law, Lussac law, again, both really dealing with the temperature aspect of it. One, obviously, volume and temperature, one, pressure and temperature. And again, really that volume either being constant or fixed or rigid is sometimes referred to, which means, again, we'll see that direct relationship of pressure increasing or decreasing with the temperature. And obviously, if the volume is sort of adjustable, if you will, that's where we were able to maintain the constant pressure with the volumes being adjusted there in Charles' Law. The next sort of relationship that we're going to look at is our good friend Avogadro. He had a number, but hey, he wanted a gas law as well. Why not? So when we think about Avogadro's number, that is our 6.022 times 10 to the 23. atoms or molecules that equals a mole, right? So it would make sort of sense here that Avogadro's law actually involves moles. So Avogadro's law is actually this guy down here, and it is basically V1 N1 is equal to V2 N2. When we're dealing with Avogadro's law, it's actually two sort of conditions that are happening, and that is at constant pressure and temperature. So at constant pressure and temperatures where Avogadro's law comes into play, N is the number of moles. So in gas laws, N is moles basically. And the relationship that we see sort of with Avogadro's law is as the moles sort of increase, so does the volume of the gas sort of the same way when we have constant pressure and temperature occurring. So there's sort of two applications of Avogadro's law that we do come across. Really, the first sort of application is just like all the other gas laws, you could plug and chug sort of into the equation there, and you could solve for a mole or a volume, as obviously one changes, the other one sort of changes pretty proportionally to it. The other relationship is with stoichiometry, and we'll talk a little bit more about it later on as well. We'll see an example here in just a second of how it sort of relates. But in a sort of gas stoichiometry problem, if you are at constant pressure and temperature, and everybody sort of in the equation there are gases, you can use sort of Avogadro's relationship, much like we use the mole to mole relationship when we do stoichiometry. So if you remember, if we have an equation like this guy here, which we could go, there's 3 moles of H2, 1 mole of N2, and 2 moles of NH3. And that's kind of just our normal sort of stoichiometry relationship that we could get from that equation. If this happened to be under constant pressure and temperature, we could do a volume to volume relationship the exact same way that we could do a mole to mole relationship. We can say there's 3 volumes of hydrogen, 1 volume of nitrogen, and 2 volumes of NH3. We could even use a unit of volume like liters, for example. So in this equation, we could say there are 3 liters of H2 for every 1 liter of N2. We could also say for every 3 liters of H2, there are 2 liters of NH3 that's produced. And for every 1 liter of N2, we get 2 liters of NH3. And those 1s and 2s, just like we get the mole to mole relationship, basically come from the balanced equation in a situation where we have constant pressure and temperature. And just like in stoichiometry problems, we could write 2 conversion factors for either of those sort of equalities. We could say we have 3 liters of H2 over 1 liter of N2, or 1 liter of N2 over 3 liters of H2. So where this could come into play and sort of useful and sort of quicker in some cases is we're going to talk about some gas stoichiometry problems a little later on in the chapter, but it sometimes will allow you not to have to use a gas law to sort of solve a gas stoichiometry problem. In a traditional sort of gas stoichiometry problem, you oftentimes have to use a gas law somewhere along the way, either at the beginning or at the end. In this case, you could actually just go right to the volume relationship to get to the answer that you're looking for without necessarily the need for any sort of gas law. So if we look at just a simple sort of example here of this reaction, we want to know how many volumes of NO can be obtained from 1 volume of ammonia. So if we turn those volumes, say, into liters, so if we had 1 liter of ammonia, which is NH3, we want to know how many liters of NO would we get. So without even using sort of a gas law, the key here is we're at the constant temperature and pressure. That implies that Avogadro's sort of law is in play here. And basically, we could just approach it like a stoichiometry problem. So we are interested in NH3 and NO. And in this case, there's basically 4 liters of NH3 for every 4 liters of NO. And that is really sort of equivalent to what we would do if we said there are 4 moles of NH3. It gives us 4 moles of NO if we were doing sort of a traditional sort of stoichiometry problem with mole to mole relationship. So because of that, we could really get right into the problem here. And if we had 1 liter of NH3, we can use this as a liter to liter sort of a conversion or volume to volume conversion. That would give us 4 liters of NH3, gives us 4 liters of NO. And I think I could do that. And I think I'm going to end up still with 1 liter here of NO. So basically here we would get the same volume of NO produced from that 1 volume of NH3. So it's kind of like a shortcut stoichiometry sort of move that you could do if you're interested in how much volume of a gas you would produce. If you're at constant pressure and temperature, you could apply really like a volume to volume relationship, just like you would do a mole to mole relationship. And the nice thing about that, like I said, is sort of will cut out necessarily the need to use an actual gas law to do the stoichiometry part of the calculation. Any questions on that there? And obviously that's an aspect of Avogadro's law that's sort of applicable to stoichiometry. And again, like I said before, you can also just use Avogadro's law as sort of punching it in like a normal sort of gas law. Any question on that there? All right, so looking at our sort of relationships that we talked about with our Boyles law, as pressure goes up, volume goes down, and vice versa, along with our Charles law, our guy Lussac's law, again, temperature increases, so does the volume to keep that constant pressure, and oppositely going down as well. And obviously our pressure in a fixed sort of rigid container like we see here, we do see that pressure going up as temperature goes up and our pressure going down as temperature goes down. And our Avogadro's law sort of incorporating moles into the relationship here with volume. So taking all these gas laws into account, Boyles, Charles, Lussac, and Avogadro's law, we do get sort of the granddaddy of them all there, which is the ideal gas law. And the ideal gas law is PV equals nRT. So the ideal gas law is a little different than all the other gas laws that we've been talking about. The first major difference is it's like a one and done situation. There's no 2 pressures, no 2 temperatures. It's basically 1 pressure, 1 temperature. There's kind of like no before and after. So that is what we use ideal gas law for. The other thing that's different is out of all the gas laws, it is the most restrictive in terms of units. So when you use the ideal gas law, in order for it to work correctly, everybody has to be in the proper units. Otherwise, you will not get the right answer. So let's talk about those proper units. Pressure needs to be in atmospheres when you use the ideal gas law. Volume needs to be in liters. N is moles, so hopefully that should be moles, or you're maybe doing something really wrong. Temperature, like all other gas laws, needs to be in Kelvin. And really the reason why all of those need to be in those numbers or units is because of R. And R is the gas constant. And R has a few different values, but the one that we use with the ideal gas law is 0.08206. And the units of R is liters times atmosphere divided by Kelvin times mole. So the good news about that is the units for R is a lot of times given to you. So you can remind you what everybody else's units need to be in so that everything cancels out correctly. A lot of books, and if you want to, a lot of people will use a rounded version of this number of 0.0821. I personally use the other number most of the time, because that's what they beat in my head and I can't get it out as much as I try. So that is the one I use, but 0.0821, a lot of people kind of round it up and sort of use that number. You're welcome to use either number, should be fine. What is an ideal gas? An ideal gas is a gases that we typically come across under normal conditions of pressures and temperatures. And there's 2 really main things that we'll talk about later on as well that make something an ideal gas. And I touched upon it earlier today. One of the things that makes something an ideal gas is the idea of we really don't look at the volume of the gas itself. We rather look at the volume of the container at which the gas is flying around in, as the volume of the container is much larger than the volume of the gas itself. So that's why, again, in a lot of problems that we come across, they talk more about the volume of the container that the gas is in, and we think of it filling it uniformly as it's flying around. So we sort of relate that the volume of the gas is negligible, and really it's more the container's volume that is most important in an ideal situation. The other major thing that makes something an ideal gas is the idea that under ideal conditions, you could have as many gases as you like flying around in the same container, in the same vicinity. They will pretty much have no interaction with each other. So there will be no repulsive forces, no attractive forces between them that could affect the pressure. So even though there may be multiple different types of gas flying around in the same container, we assume that there's really no interaction between them. And that's the other major thing that makes something an ideal gas. Later on at the end of this chapter, we'll talk about real gases where you do have to take that into account, those sort of things. But here with an ideal situation, which is most cases, you don't have to worry about those two sort of things. Any questions on that there? All right, a couple other important things here that kind of go with our friend, the ideal gas law, is another sort of terminology that we come across, and that is standard temperature and pressure, or STP. So not the little red thing, but STP, which is standard temperature and pressure. It actually does stand for two values. So when somebody says do this at STP, or this was done at STP, the pressure is 1 atmosphere, or its equivalent, and the temperature is 273 Kelvin. So when you are given that in a problem, those are the values that you should use for pressure and temperature. If it's under STP conditions, 1 atmosphere pressure, or like I said, it's equivalent, our temperature should be 273 Kelvin. Now, if you happen to find yourself at STP, there is a relationship and sort of a conversion factor that you could use when you are at STP conditions that will allow you to sort of sidestep using the ideal gas law. So if you happen to be at STP conditions, this relationship here comes into play. 1 mole of any gas will have a volume of 22.414 liters. It can only be used at STP conditions. So if it is at STP conditions, you can have 2 options to solve your problem in most cases. You can use this conversion, or you could just use the ideal gas law and put in 273 in 1 atmosphere. So you could always use the ideal gas law if it's STP conditions, non-STP conditions. If it is non-STP conditions, you should only use the ideal gas law. You should not use this conversion factor. So again, this is a conversion factor specific for STP conditions. Any questions on that there? And that is sort of how we get to our gas constant value. If you put in all the values at STP conditions, which means you have a pressure of 1 atmosphere, 273 for temperature, a volume of 22.414, and a mole of 1. There's our 0.08206 number, basically, as to where that comes from. All right, so let's give it a try here. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a volume of 5.4 liters and a temperature of 69.5. Look here. So once again, if we kind of pull out the information, we are looking for a pressure. We got moles, which is N, 1.82. We got a volume that is 5.43 liters and a temperature that is 69.5 degrees Celsius. So first off, we're kind of going through our list of formulas here. We obviously see only really one of everything: pressures, temperatures, no twos. So really this should point you to PV equals nRT, or the ideal gas law. A reminder that you always have available to you the gas constant, and also a reminder that in most cases they will not give it to you in the problem. So they won't mention anything about the gas constant or anything in a problem. So that's just something you got to keep in your head, that you always have sort of access to. And again, you can kind of the ideal gas law sort of form there. Now we want to definitely, since we are using ideal gas law, make sure unit wise everybody's okay. So obviously moles is good. Liters is the volume that we need. So very commonly milliliters to liters sort of conversion is used a lot in this sort of formula as well. And our Celsius here do need to convert to Kelvin like normal. So if we do that, we will have 69.5 plus 273. Looks like a 342.5 Kelvin. That means in this case, we are looking for pressure. So we're going to send volume to the other side on the bottom. And that's basically dividing by the volume, which would give us P is equal to nRT divided by V. Put in our number here, 1.82 moles. Our gas constant, 0.08206 liters atmosphere Kelvin mole. Our temperature being 342.5 Kelvin, all divided by our volume of 5.43 liters. Unit wise, moles cancel, Kelvin cancel, liters cancel. Leaves us atmospheres as the only unit still standing. Gives us a 1.82 times 0.08206 times a 342.5 and divided by a 543. Going to give us a 9.42 atmospheres as our pressure. Other very common thing that happens with the ideal gas law is our moles. Again, grams to moles, also a very common sort of conversion using the molar mass like we've done before. So that's also a very common sort of thing that you need to do. Any questions on that calculation there? All right, we will lay that up here for today.